about how we're going to do our moles, molecules, and grams. So if you have grams and they want to go to moles, anytime you hear the word grams, you should think periodic table. Anytime you hear grams, think, oh gosh, periodic table, yes, right? That means when you look at the periodic table, the units of the periodic table, so I'm just going to make carbon here, the units of that number is grams per mole, right? So if you ever need to go to grams per mole, look at the number on the periodic table. It's going to tell you the conversion from grams to mole. So remember, when we write this, we would write 12.01 grams per, and then people don't like it without the one, per 1 mole. Or we could have written 1 mole over 12.01 grams. That is what this number means. And so when we're doing molar masses, remember, keep at least 2 places past the decimal. But if you want to keep all 3, that's fine. Your answers will be a little bit different, but again, it's totally fine. Okay, now, if you read the number atoms or the word atoms or molecules, so atoms or molecules, that is this number right here. Right? Atoms or molecules means 6.02 times 10 to the 23rd, right? And when we write this, 1 mole over 6.02 times 10 to the 23rd, and I don't care if you use atoms or molecules. And again, you can use 6.022 or 6.02, whichever you want. Again, your answer will be a tiny bit different, but it's totally fine. Or we could write it like this. Atoms in 1 mole. Okay, so where people get confused is they'll see mole and they'll go to grams or they'll go to atoms, but they're not exactly sure where to go. So you're going to see moles all the time because look, this one says 1 mole. This one says 1 mole, right? The key is, are they talking about grams or are they talking about atoms or molecules? If you see grams, think periodic table. If you see atoms or molecules, that's when we're using Avogadro's number. So that's the key that you need to think about when we're looking at these. Okay, so we did this top one, right? This is kind of where we ended. I don't think we did the bottom one. So if you see this one says molecules. So it says calculate the number of grams of CO in this many molecules. So we want grams and we want to go to molecules, right? And so we did this one. Yes, we did. I'm just going to set it up again for you. So grams, molecules. We have to go 2 moles over to molecules, or 2 molecules from grams. Okay, so I'm just going to set this up again really quickly. Right, 6.02 times 10 to the 23rd molecules in 1 mole. And then in 1 mole of CO, there's 28.01 grams of CO. And again, this number right here comes from adding the 12. Let me write that a little neater. 12.01 from C plus the 16.00 from O. Right? And so when we do that, we get 28.01. And again, the unit is grams over moles, hence grams on the top, moles on the bottom, units, 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 units cancel, and you end up with grams of CO. Okay, so let's try another. In this case, we have grams of atoms. Remember, when we see grams, periodic table. That should go in our brains right away, periodic table. We're going to need to look there. And we want atoms. So atoms, that's always 6.02 times 10 to the 23rd. Avogadro's number should be what's popping in our head. So we have grams of aluminum, and we want atoms of aluminum. So let's say we're not exactly sure what to do. I'm just going to do aluminum here. I have my periodic table today. So aluminum, this is what I see on the periodic table, says 26.98, right? So the decimal number on the periodic table, that means 26.98 grams of aluminum in 1 mole of aluminum, right? Or again, we could write 1 mole of aluminum over 26.98 grams of aluminum. So let's say we don't exactly know what to do, but we thought about the periodic table. We want to get rid of these grams. So grams of aluminum goes on the bottom. All we're doing is looking for a unit that matches that. So that means the 26.98 grams goes on the bottom, and on the top goes the 1 mole. By the way, if you can do this faster than I can, please do it, and you're welcome to put your answer in the chat or text me your answer. Grams, grams. Now we want to go to atoms, but let's say we're not sure what to do. Here's the unit. We don't want this unit, so we're going to put it on the bottom. And we know that 1 mole equals 6.02 times 10 to the 23rd atoms. Well, here's that mole. This will go on the top. Atoms of Al. Unit cancels. And then when we do this, we can only have 3 significant figures in our answer, right? Because when we look at this, has 3 sig figs, right? Decimal place is present. Start counting from the Pacific side. 1, 2, 3, right? Once you start counting, you keep counting, right? And so let me just write this all neater, and feel free to put those answers in the chat if you got them. It's great practice with your calculators, which you're going to be using on your quiz this week. I got 2.23 times 10 to the 23rd. Yeah. Now, if you got 2.22, 2.24, all those would be correct. It should just be close to 2.23. Again, it might have been different because you might have had more numbers here, or you might have used 2, so that's fine. Again, when you're doing your molar masses, I just say keep at least 2 digits past the decimal place. So at least 2 digits. You can have more if you want, but don't round. Like, don't round this to 27, because if you start rounding all these molar masses, it will dramatically change your answer, and then you will be far off from the answer. Okay, so here's one for you to try on your own, and then we're going to go over this. So set this up if you're watching this now or later. Set this up, put it in your calculator, and see if you get the correct answer. So I'm going to give you like 2 minutes to do this, because again, this is kind of the whole foundation for the rest of the semester. If you get this the rest of the semester, not so bad, because it's all based on this. Okay, so try this, and then we'll go over it in just a minute. Oh, let me give you, that's what the periodic table says. And I'll give you that too. Okay, this, and then we'll go over it in just a minute. Okay, how are we doing? Okay, so I see lots of these coming through. So when we do this, look at what we have and what we want. So we have 0.551 grams of K, and we want atoms of K. So this have want thing kind of really helps keep your mind kind of pushed in the right direction when you're solving these problems. So want atoms. So again, one of these is going to go on the top, the other one's going to go on the bottom, or vice versa. So in this case, we want to cross off these grams, so therefore grams has to go on the bottom, moles has to go on the top. And now if we stopped, we would be at moles of K, but they didn't ask for moles of K. They asked for atoms of K. So again, the moles had to go on the bottom because we wanted to cross these units off. So therefore, this one had to go on the bottom and this one had to go on the top. Now, when we do this in the end, we need 3 significant figures, right? Decimal place is present, so we start from the Pacific, starting with the first non-zero number. So this is a 0, doesn't count. 1, 2, 3. That is 3 sig figs. So then our answer has to have 3 sig figs. Okay, so let me erase all my messiness here. Right, and so, and again, you might get like a little bit different of an answer, like you might get 8.50 or 8.48, again, just depending on your, like if you use the 2.2, sorry, if you use 2.2 here, or you might have just used 6.02. Right, so as long as it's close and about and around, we're all good. Okay, so let's try a couple more. Okay, so now let's try this top one. So I'm going to give you a minute to do the top one, and then we're going to do the bottom one together because that one's going to introduce a new little piece of information here. And you're welcome to try the bottom one on your own, but in this case, I highlighted this for a very specific reason. So try the top one, and then we're going to go over it in just a minute. And again, you can either put your answers, if you don't want to do the answers in the chat publicly, you can always just do the chat privately, the answers, or you can always text them to me on Remind. Either or is fine with me. And if you're watching this later or you don't want to, just make sure you do it on your piece of paper to make sure that you're understanding the concept. And make sure you're putting all these that you're seeing us do in the calculator to make sure you're getting the same answer. So for this top one, I'm just going to put this right here. So keep putting your answers up while I write this. We have 40.1 grams of CO2, and we want molecules. So very similar that we've been doing. So we start with 40.1 grams of CO2. And again, the CO2, we're going to get the molar mass from the periodic table. So this is 12.01. This is 16 times 2, which makes it 44. I just put them on the wrong side. 44.01 grams of CO2 and 1 mole of CO2. And we're not done because we would be ending at moles. So grams. And in 1 mole of CO2, we have 6.02 times 10 to the 23rd molecules of CO2. Right? And when we do that, put this in my calculator, which I had. So in your calculator, looking at all the chat ones right now. So in your calculator, you take the entire top times the entire bottom. So 40.1 times 6.02, however your exponent function works, which hopefully we're all good with that now. And then divided by 44.1. I got, here's what my calculator said. Oops. It said 5.48516. I'm not going to write anymore. Times 10 to the 23. Right? And so when we do that, we can only have 3 significant figures. Right? And the reason we can only have 3 significant figures is because the decimal point is present. So we start from this side, 1, 2, 3. So we can only have 1, 2, 3. We can only keep these 3. This 5 says round up. So that means 5.49 times 10 to the 23 molecules CO2. Now, if you got 5.48, 5.47, 5.49, any of those should be okay. Again, the reason is because you might have used 6.022 here. Oops. Or we did 44.01. So as long as it's close about and around, you should be fine. Just depending on these molar masses, sometimes you get a little bit different numbers. Okay, so are there any questions on that first one?
Yeah, like I used the 15.99 because I didn't round and my number was like different.
Yep. Yeah, so you could have, so again, so let me just, I'm going to make, these are going to be your periodic tables, okay?
Yeah.
So carbon is 6, oxygen is 8. And so on your periodic table, it says 12.011, and this is like 15.999. And so these are where the numbers are coming from. So if you use these whole numbers, your number is going to be just the littlest bit different than this. But that's okay. As long as it's close enough, it's okay. But like I said, you can use the full thing, but at least use 2 digits. So I always go 2 digits. So I always just round carbon to 12.01, and I just round oxygen to, I mean, it ends up being 16.00. Either of those are okay. And again, that's where that number comes from. It comes from looking at your periodic table, right? So the only way we can ever cross off grams is by looking at the periodic table. And it's the decimal number on the periodic table. That's where we get this, because remember this number, the units of this number are grams over moles, right? So that is the units of that number right there. Okay, any other questions on this? Okay, so I'm gonna leave this, but then try to erase all this. Give me a second. Now, this next one is a little different. There's a question on your final like this too. That's why I always make sure to spend lots of time on it for you. Okay, this one says calculate the number of atoms of oxygen in 40.1 grams of CO2. This one says, so the only difference in this entire, both of these problems, this one says calculate the number of, here's the difference, atoms of oxygen or molecules in 40.1, same thing, 40.1. So molecules of CO2, this means CO2, but this one is only asking for oxygen. It wants to know how many oxygens. So in one CO2 molecule, right, in one molecule, in one of these, that's supposed to be the number one, we have two, everyone agrees, there's two atoms of oxygen. One CO2, there's two oxygen here. This also means in 1 mole of CO2, we have 2 moles of oxygen, right? Both of those things are true, right? So both of those things are true when we're doing this. So if we want to know the number of atoms of oxygen, right, we could just multiply our number up here by 2, or we can put this into our stoichiometry or our unit conversion. So I'm going to show you how to do this. So we start very similar. So this time we have 40.1 grams of CO2, but we want something different. This time we want atoms of oxygen. So when we do this, I'm going to try and do this in the exact same kind of way. So 40.1 grams of CO2. Again, the only way we can get rid of grams is the periodic table. So we added the numbers up from our periodic table. 1 mole of CO2. Now here's where it's a bit different. The relationship between CO2 and oxygen is in 1 mole of CO2, there are 2 moles of oxygen, right? In 1 mole of CO2, there are 2 moles of oxygen. So we can use that as a conversion unit. In 1 mole of CO2, there are 2 moles of oxygen. Now we can do the exact same thing, go to our atoms. In 1 mole of oxygen, there is 6.02 times 10 to the 23rd atoms of oxygen. So this is the new little piece. And the reason we did that was because they specifically asked about oxygen, so they wanted to know the number of atoms of oxygen that we have here, not just CO2. So when we put that in our calculator, we still have 3 sig figs. So here's what my calculator said, 1.09703 times 10 to the 24th. Atoms. Actually, I'm not going to write the label yet because we can only have 3 sig figs. So 1 point, well, I'm just going to ask you that question. What would this be in sig figs here if I can only have 3 significant figures? Great test question, right? Good quiz question for your quiz this week.
1 point.
1 point. Yeah, so,
10.
Yep, there you are, 1.10. So I'm going to use a different color here. So that's what I'm stopping at. So this 7 says round up. Well, when you round up a 9, it ends up rounding this one up. So it ends up being 1.10 times 10 to the 24th. And yes, you have to have this 0 because this needs to be 3 significant figures, right? Decimal place present, 1, 2, 3 significant figures. And then don't forget this piece right here. A lot of times we forget that piece because it's on the edge of our calculator and we just forget it. So that would be our answer. So again, this is a little bit different because we added this new little train track, that's what we call those little train tracks, to this type of problem. But you can see these are the same, and these are the same. The only difference is we didn't go to CO2 here, we ended up going to O. Okay, so let's try another one like this. Okay, so I'm going to, I think I give you the first, don't I give you the first 3 lines of this? Did I give you the molar mass on your notes? I keep trying to change that, but I did, yeah, I know. I gotta remember to change that. So I give you the molar mass. So I'll just put this on here since I give it to you. And again, this number comes from the periodic table, from the periodic table, from the periodic table, right? Because there's 3 carbons, there's 8 hydrogens, and there's 1 oxygen, right? This is the molar mass of hydrogen, the molar mass of carbon, because there's 3 carbons and 8 hydrogens and 1 oxygen. So this is the molar mass. And I'm going to give you these. All right, so now I want you to try this one, and then we're going to go over it again in just a minute. So try this one, remembering this is kind of the little new piece of this one. We'll do this one in just a minute. So set this up, and then we'll go over it. How are we doing? Do we need another minute? We're ready. All right, I'm seeing some of these come through. So if we start with 72.5 grams of C3H8O, then we use our molar mass, 60.09, I did not need enough room, grams of C3H8O in 1 mole of C3H8O. And I know it is so annoying to write that whole thing, but it's very important. So if we look at our units now, this one crosses off, this one crosses off. Now we can go from moles of C3H8O to atoms, right? So I'm going to say in 1 mole of C3H8O, there are, they ask for hydrogen, there's 8 hydrogens. So there's 8 moles of hydrogen. Now I'm at moles of hydrogen, but they asked for atoms, so I have to keep going. Remember, whenever we see the word atoms, we think Avogadro's number. 1 mole of H, 6.02 times 10 to the 23rd atoms of H. Okay, and then we check our units. Now again, sometimes people try to put H2 here. It's only when it's by itself. This hydrogen is absolutely not by itself. It is right here in this molecule, right? So even though we're taking it out, it doesn't mean it's diatomic, right? It's a part of a molecule. It's bonded to the C's and the H's, I mean the C's and the O's. Okay, so when we do this, in the end, we're gonna have 3 significant figures, right? So, well, I'll just put all this meter right here. It's the exact same thing, it's just much prettier. Units, and we end up 5.82 times 10 to the 24th atoms of hydrogen, right? And again, as long as you got about and around, that's fine. Because again, on this one, look, I use 6.022. Oops. Sometimes I do, sometimes I don't. I just want you to be used to seeing them both ways, 6.02 or 6.022. Okay. And then I rounded here because I ran out of room. Probably should use 60.09. Okay, so again, the difference here is we started with a big giant molecule, but they only want a piece of the molecule. They just want the piece. And so how we do that is in 1 mole of this, there are 8 hydrogens in here because we can see there's 8 hydrogens. And so we take them out and then we just finish our problem. So this is the same as we did yesterday or on Tuesday. This is the same as we did on Tuesday. This is our new little piece here that we're talking about today. Okay, so let's try another one. Okay, so for this one, what mass of MgCl2 contains 6.02 times 10 to the 23 Cl ions? Okay, so, and I put this one on here because it's worded a little differently because you're going to see these worded all sorts of ways. And so we really need to figure out what we have and what we want, right? So a lot of times we're like, oh my gosh, I don't even know where to start. We start with the number they give you, right? Look, they're giving us 6.02 times 10 to the 23rd Cl ions. So I say we start with that. Okay, and if we look here in this, there's 2 Cl ions in one of these MgCl2. So there's in 1 mole of MgCl2, there are 2 moles of Cl. And I'm okay if you forget to put this little ion sign here. That's fine with me. Now again, these ions, this is the same as think of it as atoms or think of it as molecules. Right? Any of those, they're kind of interchangeable. Just ions is charged, atoms is a single element. But if in your math you mix it up, it's fine with me. Okay, so, and we're gonna go to mass. Remember, mass is grams. Okay, whenever we see the word grams in our brains, we need to think periodic table. So when we do this, I'm gonna make a periodic table for us. Here's Mg, and here's Cl. Cl says 35.45. Mg 24.31. So Mg is 24.31 plus 2 CLs, 2 times 35.45, which gives us 95.21. And remember, these units are grams in 1 mole. So grams of MgCl2 in 1 mole of MgCl2, right? So that's our molar mass. Oh, and there's your molar mass right there. So that's how we get our molar mass. Okay, so now I'm going to erase my little mini periodic table we've got here. We got all that. And again, if you can do this faster than I can, go ahead, put it in the chat. So there's 6.02 times 10 to the 23rd Cl ions, or ions of Cl, in 1 mole of Cl. And then we use our relationship. There are 2 Cls, 2 moles of Cl for every 1 molecule of this. Now we can go to grams. In 1 mole of MgCl2, there's 95.21 grams. Right? And so then when I did this, I got 4. Well, you know what? I'm gonna wait. I'm gonna put everything on there. Okay. So again, put this in your calculator, even if you didn't get it set up. Put in your calculator and see what you get. So ions, moles, moles, moles Mg, moles Mg. Are you seeing how important it is to put these labels like Cl ions versus like moles of Cl and MgCl2? And I know that sometimes people think, oh gosh, all these labels take so much time. I'm telling you, hours. It will save you hours and hours of pain and anguish and frustration if you just write all of the labels with the units. It will save you so much time. Speaking of that, I forgot to put this one on here. I'm going to do it in red while I'm waiting for everyone to put this in their calculator. Okay. So when you put in your calculator, it's the entire top divided by the entire bottom. And you end up with 47.620811561. But we can't keep all these numbers, right? We need to decide how many sig figs can we have, right? Your number of sig figs is always going to come from your problem. It's always going to come here. It's not going to come from any conversion units you found. It's going to come from your problem. So this is the only number we have. This has 4 sig figs, right? Decimal places present. 1, 2, 3, 4. This has 4 sig figs. That means our answer can only have 4 sig figs. And since this is a 0, it says leave it alone. So this would be 47.62. And again, here's our unit. Grams of MgCl2. Okay, that was a tricky one. Any questions on this one? Questions on this one? No? Okay. So here I'm gonna. Okay, go ahead.
How can you differentiate between that new piece of information they give us, the 1 mole of MgCl2 over 2? So how do you know which one goes on top, which one goes on bottom?
Great question. It is completely determined by your units. So for example, in this case, Cl ions had to go on the bottom because we needed to get rid of them. The only option, remember, when you use this number of 6.02 times 10 to the 23rd, the only option you have for the other side is 1 mole. Right? So since we had 6.02 times 10 to the 23rd ions here, we had to put 1 mole on top. Since 1 mole was up here and we don't want this, right? We want to get rid of it. Since we want to get rid of it, that means we have to put that same unit down here. And so since we had to put moles of Cl here, that means we put 2 moles of Cl because there's
Oh,
2
that's
Cl.
okay. I see it now.
And the other side goes on the top. So you always know where it goes because you're trying to get rid of the unit.
I understood. Thank you.
Yeah, and that's why these labels are so important. So I know there are some of you who are like, oh, I don't want to write all these. I can do it without that. It only gets more intense and there's more problems after this. So you might as well just put the labels in now. It'll make your life so much easier later. Okay, so same exact thing, just neater. Okay, so let's see here. Oh, hey, this next one was a quiz question that in my test last semester. A quiz question. This was a quiz question I had last semester. I put it in the lecture this year. Okay, so this is exactly, by the way, what your quiz looks like when you take this. Very similar. So how many moles of aspartame, this is like that artificial sweetener, are found in 40.0 milligrams? And question number 2, how many molecules of aspartame are found in this mass? So we have 2 problems here, right? So I'm going to separate both of these. So we have milligrams, and I'm just going to call this ASP, okay? Because I don't want to write the whole thing. And we want, let's do the first question first. We want molecules. Molecules of ASP. Okay. Well, here's a little, right? Little curveball. Milligrams, oh, unit conversions. Yep, we got to know these, right? And so milli means 1,000. So there are 1,000 milligrams in 1 gram. How did I know that? Because I memorized it, which you will also be required to do, right? So I'm telling you now, but you need to know that that is the conversion. Okay, so let's start with, again, what they give us. We start with 40.0 milligrams of, again, I'm going to abbreviate it. Let's say we have absolutely no idea what to do, but we do know we need to get rid of this unit. So we're going to put it on the bottom. Well, we can't do anything with grams. We want to go, oops, this is moles. We want to go to moles. Our first one, we'll go to this one first. We want to go to moles of this. Well, the only way we can go to moles is using grams or molecules. Milligrams is not part of that at all. So we have to get rid of these milligrams. So I'm going to put this one on the bottom because it matches with the unit. Right? This whole piece will go on the bottom and the other piece will go on the top in 1 gram of aspartame. Cancel, cancel. Now we can go to moles. In 1 mole. So anything wrong with what I've written so far?
Yeah, it should be grams.
Yeah, very good. See, grams here, same unit must go on the bottom, right? That's what's going to determine your unit on the bottom is whatever you're trying to get rid of. So grams of aspartame, and then 1 mole will go on the top. Keep an eye on your units, right? You're crossing off your units. That's how it works. Now, how do we get this number? Is it just 1 gram? How do we get that number?
Do we have to calculate out the CHNO?
Yep, we have to use the periodic table. So I'm just going to make a little periodic table for you in case you don't have one. I have now memorized carbon. Here's hydrogen. Here is nitrogen. and oxygen. Okay, so we have to find that molar mass, right? So in this molar mass, it's a doozy. You have 14 carbons, 18 hydrogens, 2 nitrogens, and 5 oxygens. So I'm going to give you a minute to add this molar mass, because this is as hard as molar masses get. Right? They don't get more difficult and big than this. So let's see them, make sure that we're good with our molar masses, and then we'll keep going with the problem. I'll write it down here while we calculate it. So it is, whoops. Maybe I'll do it up here so we have enough room. So 14 times 12.01 plus 18 times 1.008 plus 2 times 14.01 plus 5 times 16. I really don't know what this molar mass is. So I'm going to agree that's 294.298. We're going to agree with it a little more. I have it on here in a second. I got close to that. I got 292. So, okay, so we'll say this molar mass is 294. Omar agrees with himself. Okay, I'm just gonna look and see what I calculated. I got 294.34. Again, that might be not exactly there, depending on how many sig figs I used, but close enough. Okay, so now when we finish this, we get moles. Right, and now how do we know to stop here? Right, that's another issue. How do you know when to keep going? How do you know when to stop? That's where this comes in so handy, right? If you have written what you want. Now, some people, they like to go like this, like, oh, I'm gonna go to moles, or they'll put like a little star here. I literally write want, like, what do I want? I want moles. That's how you know when to stop. Right? And that's really important because pretty soon you're going to get so good at this. You're just going to fly through these and you're going to continually give me the right answer to the wrong question, meaning you're just going to keep going to molecules. And I'll be like, I didn't ask for molecules. I asked for moles. Right? So you need to know where to stop. So keep an eye on. That's why I like to do this, because it helps me keep an eye on where I need to stop. Oh, look, I'm at that unit. That means I'm done. Okay. So when we do this, 40 divided by 1,000 times 294.34. Here's what my calculator says: 1.35897 times 10 to the negative 4. Okay, practice for our quiz. I can't have that answer. How many significant figures can we have?
2, 3.
Yeah, we can only have 3. Again, why is that? Because this number decimal place is present. So we start with the first non-zero number, 1, 2, 3, 3 sig figs. So stop there. This 8 says round up. So then we end up with 1.36 times 10 to the negative 4. And again, we have to have our unit here, but we conveniently wrote this right there, moles of ASP. Okay, so that would be our moles, right? That was question number 1. Now we have to do question number 2. Question number 2, ask for molecules. So I'm going to erase all this. I'm just going to do question number 2 right below it. So really, we could just kind of keep going here and do another train track, but I'm going to set it up just so you can see how similar this is. It's just one more tiny step. So same thing. I'm just going to go one step further 1 gram of ASP and 1,000 milligrams of ASP. 294.34 grams of ASP, 1 mole of ASP. So see, I just copied down that I did on top, but now I want molecules, right? We want molecules this time because this is the second question. How many molecules do we have? So remember, whenever we see the word molecules, we think 6.02 times 10 to the 23rd. Right, that's the number that pops. Whenever we see atoms, molecules, ions, this is the number that's going to pop up into our brain. And in 1 mole of anything, there are 6.02 times 10 to the 23rd of it. Molecules ASP. So it's just one tiny bit more step. And I don't know what you get when you put this in your calculator. Put this one in your calculator and let me know what you get. This is a great practice one. Great for your quiz today too, because it's got so many calculations on it. So let's try it. Just put this in your calculator and let me know what you get. So I got with sig figs. I'm just going to go straight to 3 sig figs. Actually, I won't. Okay, I'll put a little bit more on there. 1810 times 10 to the 19th. Right? But again, we need to have 3 sig figs. Because this had 3 sig figs. So we keep those. It's a 1, so we can just ignore it. Times 10 to the 19th molecules of ASP. And again, if we look at our units, which we've all written our units very beautifully, grams, grams, moles, moles, that's the unit we wanted in the end. Check. That's the unit we ended in the end. So again, for your quiz that's next week, you're going to actually have to show all of this work, right? And this is how the grading will often work if it's free response. This would be 2 points. I'm just going to write +2, +2, +2, +1 for the answer, +1 for the unit, and +1 for the right sig figs, right? So if you don't have any work, the best you can get is 3 points, and you lose 6, right? And for your work, again, you need to have the whole piece. You can't just have the one. You need to have, you need to have the whole entire piece. Okay. Any questions on these? Okay, I'm going to walk you through these meter again, just so you can see. So on this one, I just went from grams, milligrams to grams, and then we found this. Here's how we got to that molar mass. We just talked about that. And again, 14 times 12, 18 times 1, 2 times 14, 5 times 16, right? And this piece, I separated out into individual pieces. So here's our moles, and then I just did it a little bit different, and then I got molecules. It's the exact same thing. As long as your units follow, your answers are, if your units follow, and you've written your units down correctly, you will always get the right answer, assuming you put it into your calculator correctly, right? So the whole calculator issue can be an issue. Okay, so how are we doing on moles, molecules, and grams? Pretty good? Again, I think yeah, it's kind of fun, right? I think that, sorry, I'm gonna hurt your eyes for a second. This little piece right here, this is very handy when you get started, right? It's very handy because like saying use your molar mass, use the periodic table, Avogadro's number, and it's written right here, really helps guide what you're supposed to do. So I always say when you're starting this, like when you're doing your Chem 101 homework, to like have this slide right there while you're doing it, because I think it really helps in the beginning. By next chapter, you're going to be doing these literally with your eyes closed, like so fast. You're going to have them done with the answers before I can even write them down, just because you're going to do so many of them. And again, this is kind of the basis of like 90% of the rest of chemistry is literally just doing variations of this exact thing. It's just crossing off your units. We just start adding more things to it, but it's the same basic principle. Okay, so now we're going to do one more thing, and it is doing empirical and molecular formulas. So when we're doing empirical and molecular formulas, we're just trying to figure out what we get with these empirical and molecular formulas and how do we get to them. Okay, so let's talk about what an empirical formula is. So just a quick little like definition kind of a thing. So we call like MgCl2, we call this a formula unit. Often you're going to call this a molecule. It's fine. Technically, because it's ions, it's called a formula unit. CO2, right? Because this is a metal, non-metal. This is an ionic compound. So we call ionic compounds formula units, or we call covalent compounds or molecular compounds from two non-metals molecules. If you call this a molecule, I'm never going to count that wrong. But just know they are not the same technically. Ionic compounds are called formula units. Molecular or covalent compounds are called molecules, right? So it's just a little like side note about that. Okay, now empirical formulas. So an empirical formula, it just expresses the simplest whole number ratio of atoms in a compound. A molecular formula is how it actually exists in nature. And so you can have the same subscripts as the empirical formula or some multiple of them. So for example, if you had let's see here, C4H4, right? You could simplify that. CH, that would be the empirical formula. It's the simplest way to write a compound. So for example, we have C6H6 or C2H2. We can simplify both of those, right? If I simplify this, C6H6, that would just simplify to CH. If I simplify C2H2, that would simplify to CH. These are empirical formulas, the simplest way to write something. Now this, H2O2 and H2O, right? We could simplify this one to just HO. We can't simplify this one, right? Because it has to be whole numbers. And there's two H's and one O, so we can't simplify this one. So this one has the same empirical and molecular formula. So these are the molecular formulas. The simplest way to write it, that is the empirical formula. Right? This is how molecular formulas in nature, that's what it actually is, right? So it actually is this in nature. This empirical is just the simplest way to write it. Water has the same empirical and molecular formula because water exists as H2O in the real world, and you can't simplify it any further. So it has the same empirical and molecular formula. So let's look at a couple more of these. So if I was going to simplify this, C5H10, this is again a molecular, the way it exists in nature. Empirical is the simplest way you can write it. So all we did, right, we crossed that out and made it a 2. Same thing here, look, they have the same empirical formula. All three of these have the exact same empirical formula. They're not the same molecule, they just have the same empirical formula because when we simplify them, they simplify to the same thing. But if we look at this hydrogen sulfide, can't simplify it. So its molecular formula and its empirical formula are the same. right? Now, ionic compounds have no molecular, they're all, right, when we write an ionic compound, we always write it as simply as possible. So they're automatically always into the empirical formula, which is like lovely for us, just because we always write them as simple as possible, right? We wouldn't write Na22Cl22, right? We wouldn't have never have done that. We would have simplified that to NaCl. Okay, so let's practice a couple of these. Okay, so we're going to see if they have empirical formulas for this one. Empirical formulas, if you can simplify anything, you can simplify it. So it doesn't matter if it's like a polyatomic ion, a molecule, doesn't matter. If it's able to be simplified, you can simplify it. Okay, so how about this CH2Cl2? Can this be simplified? Right, so we have one carbon, two hydrogens, and two chlorines. So yeah, we can't simplify this one because we have one carbon here, so it's not simplified. Can we simplify this one? If we can simplify it, what would we simplify it to? So what would this one be? Waiting for a few of them. Yeah, so we're getting this. C2HCl. Yeah. Okay, how about, can we simplify this? HGO. Yeah, we can't, right? It's already as simple as it gets. So it would have the same empirical and molecular. How about this one? What would this simplify to? Yep, HCO2, very good. Right, so again, the ones that we're simplifying, these are the molecular formulas. These are the empirical formulas. That was supposed to say empirical. These are the empirical formulas. Okay, how about this? Can we simplify this? And if we can, what can we simplify it to? So you're seeing it. I see how fast you're going on these. Yeah. Okay, so how about that one? That one's going to take a little bit more thought. You might have to rewrite this one. So I'm going to rewrite this for you so you can see it. So there's a carbon and there's a carbon. So that means we have two carbons. There's three hydrogens. There's a fourth hydrogen. So we have four hydrogens. And we have two oxygens. Now when I write it like this, now you can see how to simplify it. Yeah, so sometimes, and especially with organic molecules, this is how we write them. We write them because this is how the actual structure is. So this is the actual structure of it, and this is why we write it like this. And by the way, you are going to be amazing at this structure. By the end of the semester, you'll be able to do exactly what I did. And so that's why we write it like that, because we're showing the structure. And yes, it does simplify CH2O. Okay, this one, and 2H4, what would that simplify to? Yes, NH2. How about our C2H6? What would this one simplify to? So you see how when we simplify them, again, these are the empirical formulas. That is the molecular formula. CH3, all right, how about this one again? Think of what I did with this one up here when you're doing this one down here, right? Combine them. Right, so I'm gonna write it. So you gotta just literally just combine them. So there's one carbon, two carbons, three carbons. Oops. And then there's 2, 3, 4, 5, 6 hydrogens. So yes, it combines to CH2. And again, we write them like this because this is what it looks like in real life. Right, so that's kind of what it looks like in real life. Simply there's a double bond right there. But again, We'll be doing that at the end of the semester, not the beginning. Okay, last one. What does this one simplify to? Yes, look at Ocker, right? So the ones that are, again, these, the ones that are not highlighted, those are the molecular formulas. All these highlighted ones, those are the empirical formulas. Okay, so we're good with that. So now what we're going to do is we're going to try and figure out how we get these empirical formulas. So, and then from there, we're going to learn how to find the molecular formula. Okay, so empirical formula. Remember when we did this Tuesday, right? We did this on Tuesday when we did percent compositions. We can use those percents to go backwards to figure out the empirical formulas. So for example, here is, I told you we're going to come back to this problem. So here is, remember we had the grams and we found the percents of these. So we're going to use these three numbers to figure out the empirical formula. So again, we're going to find out these formulas. So the ones in the yellow, this is what our goal is to do, is try and figure out how do we know how many, right? How many S's are there? How many CUs are there? So like, how many S's are there? How many CUs are there? And how many FEs are there? That's what we're going to try and figure out. And we're going to do that from these percents. So now when we're doing empirical formulas, it's really important that you follow these rules. So I'm going to show you these rules, and then I'm going to actually go back to that problem and show us how to do it. So rule 1, if you have a percent, just assume that's grams. So if you have 34.9%, you're going to assume you have 100 grams. So that means you've got 34.9 grams. That's step 1. Assume 100 grams. Step 2, convert grams to moles. Grams to moles, right? So we do that using our periodic, that does not look right. Our periodic table. Step 3, divide everything by the smallest number. This one I'm going to have to explain a little bit because you're like, what? And then here's a special case. If the fractions are encountered, you multiply by a common factor to get whole numbers of each subscript. Again, a little bit tricky on there. Okay, so let's try this with this case up here. And I'm going to write all these rules again. And highly suggest you write these rules down somewhere. So 1, assume 100 grams. Okay, so therefore, if we have S and we have CU and we have FE, that means we have 34.9 grams of S. And we have 34.6 grams of CU. And we have 30.5 grams of FE. That's step 1, right? Step 1, check. Step 2, convert all of them from grams to moles. So see, I'm doing it like a little factory here. It's an empirical formula factory. And again, the only way we can do this, go from grams to moles, is to use our periodic table. So I'm just looking at that decimal number on the periodic table, grams of S and 1 mole of S. Cu, 63.55 grams of Cu and 1 mole of Cu. Fe is 55.85, oh, that's supposed to be an 8 grams and 1 mole FFE. Sorry, trying to write this as neat as I can. Okay, so this is not on a page because I'm just walking you through it. We're going to do like 15, not 15. We're going to do a lot of these. Okay, so that's step 2, convert from grams to moles, right? Oops. So don't use sig figs. This is the only time in chemistry I'm ever going to tell you, don't use sig figs. Okay, don't use sig figs here. So if we have 34.9 divided by 32.07, again, I'm just walking you through this so you can see these steps. This is what my calculator says. I'm going to leave it to 4, whatever. I'm not using sig figs. See, I'm not even going to consider sig figs. And when you do this, this is the only time ever in chemistry you're going to hear me say, don't use sig figs. And we're going to do this problem again in a few minutes, so you don't have to worry about writing it down. Okay, here's step 3. And this is the one I want to show you. Step 3, I write divide by smallest number. Okay, so I'm going to go back up here. So we divide each of the mole amounts from step 2 by the smallest mole amount, right? The new numbers are our subscripts. So what does that mean? Which number is the smallest? Right? That's literally what you go. You're like, oh, this number is the smallest, right? That is our smallest number. You divide all of them by that number. Okay, so that means this is what number 3 says, divide by the smallest number. This is our smallest number. This is what we divide by. 4, 4, 5, 3, that equals 1. And you divide all of them by that number. This is about 1. 5, 4, 4, 5, 3. And I think that equals like 4-ish if I remember. 8. It equals 1.9987. That is about 2. That is close enough to 2. Now, these are the subscripts of, remember we were trying to figure out like S, what is it? CU, how many? FE, how many? This is how many. So this means we have 2 S's, we have 1 CU, and we have 1 FE. So what we did is we just found the empirical formula, right? So again, only time ever in chemistry, I'm going to tell you to not use your significant figures. I would go at least 5 to 6 places past the decimal point, and when we get to harder problems, you will see why. Okay, so let's try another one. So now this next one is going to be on your paper. Okay, so here's our percentages. Remember, where can I write this? Step 1, assume 100 grams. Step 2, grams to mole. Step 3, divide by smallest number. Okay, so let's try this. So we have K, Mn, and O. Step 1. Step 1. And see, I kind of do it like, literally kind of do it like a little, I call it like a little factory. Now remember, this O is not diatomic, right? It is not by itself. It is part of some kind of is part of some kind of thing. So we have K, some number, Mn, some number, O, some number. Those must be question marks, right? So it's not diatomic because it's not by itself, right? It is not by itself in this case. Step 2. Just going to do this so you can see these are different steps. this is when we look at our periodic table and we use the molar masses. So this is 39.10 grams, 1 mole of K. Mn is 54.94 grams of Mn, and 1 mole of Mn. Oxygen is 16.00 grams of oxygen, 1 mole of oxygen. And then you put them all in your calculator. Right? And we don't think about our significant figures at all. So on this one, again, I say go at least 4 digits. At least 4. 5 is better, but, and you will see why next week. And if you can finish this before I can, please do. 63287, 1.51 divided by 16. Okay, that's step 2. Step 3, divide by the smallest. Let's do this one in light blue. So you pick out, okay, well, which one is the smallest number? Well, this one is barely the smallest. What is the smallest? And again, whatever you do to one, this is why I kind of treat it like a machine, you do to them all. This is the step, by the way, that everybody always forgets. So this equals almost exactly 1. And 2.531875 divided by 0.63287. This equals 4.0006. I think we can call that 4. Right? These are the numbers. These are the numbers of our empirical formula. So we have 1K, we have 1 Mn, and we have 4 O's. That is the empirical formula, right? So it's kind of fun, I think. You just have to remember the steps, right? And there is another step that we are going to do, but we are not going to do that step today. Okay, so I'm going to walk you through this again without my fun colors.
Quick question, Professor. On your end product, I noticed that most of the results end up being whole numbers. Is there any situations where you're going to be given like a 3.5 or a 3 point?
Yep, that's the extra. That's the step 4 that we haven't gotten to yet.
Okay.
Yeah, that happens all the time, actually. So right now, that's why I'm giving you all the easy ones, because the next step is kind of, it puts a little twist in it. But yes, we're going to start that right away on Tuesday. Okay.
Thank you.
Yeah, I'm giving you easy ones right now. So here's the first and second step. We assumed 100 grams. Again, then we got the moles. And again, these numbers came from the periodic table, right? That's where those numbers come from. We get our moles. So that's step 2. Step 1, assumed 100 grams. So we turned them into numbers. Step 2, got our moles. Step 3, find our smallest one and divide by our smallest. So let me just go back. This is our smallest number. So we're going to divide all of our numbers by that number. And they all ended up being pretty perfect. And so we have KMNO 4. Okay, so that's your first glimpse at our empirical formulas. Now remember, I'm just going to go back a second. All we did right now is we just found the empirical formulas. We still have to figure out how to get to the molecular. So we just found this, and now we have to go to that next. So we have a little bit more to go before we do that, but we're making progress.